So let's go ahead and just get a little start on our chapter 7 and 8. So if you need a minute to go ahead and get out your notes for chapter 7 and 8, go ahead and do that. All right. All right, so here we're talking about quantum mechanics, which is not nearly as scary as it sounds. So here we're going to talk about basic ideas of quantum mechanics. And the first one is one you've probably heard if you've taken some physics, and that is wave-particle duality. So sometimes we think of light as a wave, and sometimes we think of it as a particle. So what we're going to see is that light, we can break it down to little particles that we call photons. But those photons move in space as a wave, and that's why we can think of light as a particle or a wave. And again, the wave is just a stream of those tiny particles. And light can also be thought of as electromagnetic radiation. So this is more fun when I'm in class with you and I can point up to the lights, but wherever you are, if you look at the lights or you look at the light coming out of your device, that is electromagnetic radiation. So you can always scare people a little bit and be like, dude, I got really bad electromagnetic radiation exposure today. It just means that you were in light. And that could be sunlight, that could be the light from your phone, that could be the light from your computer, it could be the light from your refrigerator or in your room. All of that qualifies as electromagnetic radiation. And just because it has the word radiation in there does not mean it's dangerous. So that is just what it's called. It is electromagnetic radiation, also known as EM radiation. So here is light as a wave. So we'll be talking about something that we call the wavelength, and we'll be using this symbol called lambda, and we'll see that in our lab today. So again, that's the wavelength, also known as lambda. And the wavelength is the distance or I should say the length of the wave. So sometimes we think of it as crest to crest, which is the top of one wave to the top of the next. You could also think of it as trough to trough, the bottom of one to the bottom of the other. But either way, it is essentially the length of that wave. We're also going to be talking about frequency. And frequency is the number of cycles or wavelengths per second. So when I'm thinking about frequency, I know this is bad artwork, so you're going to have to bear with me here. Let's say you were magically standing on top of the water in the ocean, and here you are magically standing on the ocean, and you're going to count every time a wave passes you. The number of waves you can count in 1 second, that is the frequency. So how frequently do those waves pass you by as you are magically standing there on top of the ocean? And then down here we have talked about the wavelength, and the wavelength, that symbol is called lambda. Frequency, that symbol, it looks like a V, it's actually called nu and u. But those are the two symbols that we're going to be looking at, the two variables we're going to be looking at, frequency and wavelength. So any questions on frequency or wavelength here? All right, so light is a wave. So here we have light, and we have a huge variation. So here we have these nice long wavelengths, and eventually as we move to the other side, we have these nice short wavelengths, very, very high in energy. So if I look at the long wavelengths, these are low in energy. And these are things that are not dangerous to us. So things like radio waves, microwaves, infrared radiation. I know some people worry about microwaves, but they actually have less energy than the light that's coming out of the light bulb, the light that's coming out of your computer screen right now. So all of this is low energy light. What's right in the middle here, this is the visible light that we see. So it's expanded out because, like everything we humans do, we think what we see is the most important. So it's really a very, very tiny amount on the spectrum. It goes from about 400 to 700 nanometers, but these are all the lights that we see, starting with red at the low energy side and violet at the high energy side. And tonight's lab, we're going to get a chance to talk a little bit more about these colors. Once we pass violet, then we go into high energy light. And these are things that you've very likely heard of. So here we have ultraviolet radiation. This is the UV radiation. So if you buy sunglasses, they are there to protect you from UV radiation. If you buy sunblock, if you put on makeup, if you have contact lenses, all of that is UV radiation blocking. So it's all to protect you from that ultraviolet radiation, which we know can cause skin cancer and other types of cancers. So UV radiation, that is high intensity light, and that is light that can definitely cause us damage. Then we have x-rays. And most of us have had an x-ray once in our lives. If you're lucky enough that you've never broken a bone, you may have fallen and they suspected you broke a bone and you got an x-ray at the doctor's office. So one x-ray, as you probably know, is not a big deal. However, if you're going to get a lot of x-rays, then it becomes a big deal because that is high energy radiation. So if you've ever had that x-ray, the person who helped you out, your rad tech, probably had a little badge like so on their uniform, and it's not just to identify who they are, it's actually a radiation badge. And so those badges, usually once a month, but if they were around a lot of radiation, it might be once a week, they get analyzed to make sure that person doesn't get too much radiation. When I was in grad school, we used uranium, we used a lot of radioactive materials, so we had a badge that we had to wear over your heart, and we also had one that we wore on our hand. It was a ring badge, and those do get analyzed once a month to make sure we didn't get exposed to too much radiation. So x-rays can be extremely dangerous if you get a lot of them, but the kind that we use in medicine, those ones are fairly safe as long as you're not getting too much exposure. If you're getting an x-ray every day, that could be a problem. But hopefully you don't break your leg that often. All right, so next up over here are gamma rays. And we talked about gamma rays once upon a time. Way back, I believe it was chapter 1, we talked about alpha, beta, and gamma. Gamma are the most intense type of, gamma rays are the most intense type of radiation, and they are the most dangerous. So when we're talking about plutonium and other types of very dangerous radiation, they are kicking off those gamma rays. And I do see a question. So there could be colors that we can't see. So yes, anything that is essentially either above 750 nanometers or below 400, we cannot see them. But other animals and sometimes insects can see those. So yes, there are colors that we can't see. All right, so questions about anything that we've talked about so far? All right, so here is sort of a overview of, on the left-hand side, our low energy waves. So our low energy waves have a long wavelength. So if you imagine that you are that magical person and you are, cruising along in the ocean, just standing over the waves, this is a nice sloping wave, is a nice relaxed wave. And so these are going to be our low energy waves. They have a long wavelength, meaning that there's a big distance between one wave and the next. And it's low in frequency. So if you were this magical person and you're hanging out on top of the water and you're counting the waves as they come past you, you're not going to be able to count very many per second because they're coming very slowly at you. But on the other hand, over here, this is our high intensity light. So if you're over here, and let's say you are that magical person standing on top of the wave, these waves are coming fast and furious at you. So they are coming one after the next after the next. They have a very high frequency, and if you were to measure the distance between waves, it's very short. There's very little distance between the waves, and they are coming at you very, very, very quickly. So again, we have the high energy, which will have a short wavelength and a high frequency, and the low energy with the long wavelength and the low frequency. Sometimes students find it helpful to remember it just in terms of low energy means high or long wavelength, and low frequency. So low energy goes to low frequency and a high or a long wavelength. On the other hand, if you have high energy, you're now going to have a low or a short wavelength, and you will have a high frequency. So sometimes it's helpful to just remember it in terms of symbols. But any questions on anything here? All right, so here is just one more image similar to what we saw before. So here we have the nice sloping low energy. And again, low energy has the long wavelength, big distance between the waves, and it's a low frequency. They're not coming very fast. And over here we have the waves that are coming very, very fast. These are high energy. They're short wavelengths, and they are high in frequency. So they're coming fast and they are close together. So if you were on a boat in the ocean, you do not want high energy waves coming at you. You want those nice, slow, low energy waves. Or if you're a magical human who can stand on top of the ocean, you want low energy waves coming at you. You don't want the high energy waves. All right, so questions on anything here? All right, so we've been talking about the idea of wave-particle duality, and I want to let you know light is not the only thing that can do that. Electrons also have a wave-particle duality. So electrons are particles, and that's how we usually think of them, but they have some wave-like properties. And one of those is that electrons can diffract. So we talked about X-rays a little while ago. There is a machine, an X-ray machine, and that machine is actually how we find out what our atoms, what our crystals really look like. So you might have looked at some of the images in a textbook of, say, NaCl or calcium chloride and say, well, how do they really know that's where the atoms are? We actually do it through X-rays, and they're very intense X-rays, much more so than the X-rays you would get in a medical situation. When I was in graduate school, we did use X-ray crystallography. We called it XRD, X-ray diffraction, because we are using the diffraction property of electrons. And just like when you're first learning to drive and they make you learn all the horrible things that could happen if you were in a car accident, they make us watch the video of a reenactment of a person who put his hand into the X-ray beam. At first he didn't know anything was wrong. By the next morning his finger was black and he ended up having to have his finger amputated. So the X-ray beams that we're using in chemistry are much more intense. And if you're wondering, yes, those machines are locked down with a key, and if you open the lid, it is supposed to automatically shut off those X-rays so nobody could possibly get their hand in there, so we would never have that mistake happen again. But what these electrons are doing is they are diffracting. So once we hit the atom with an X-ray beam, let me grab a better color. So we hit the atom with an X-ray beam, what we see the electrons do is this diffraction pattern. And so if we do this to two neighboring atoms, we get that diffraction pattern, and we do this with a computer, and the computer looks at where they intersect, where all these little lines here intersect, and from that we actually back calculate where the atom must have been, and that's how we figure out the structure of our crystals. So it's actually a very involved process. It's not as simple as just shooting an X-ray the way we do when you're at the doctor's office. But I show you this not because I want you to become experts at X-ray diffraction, but because I want you to know that it's not only light that has this wave-particle duality, that electrons are also particles that have wave-like properties. Any questions on this one? As a grad student, I spent many nights up all night trying to find a perfect crystal, and we do call them perfect crystals, and we mount them on a glass fiber, and then we set them to go on the X-ray all night long, so it's literally taking an X-ray for 6 or 8 hours. All right, so next up, calculating frequency. So here says yellow light given off by a sodium vapor lamp used for public lighting, and it has a wavelength of 589 nanometers. What is the frequency of this radiation in hertz? And I gotta tell you, we don't use sodium vapor lamps anymore, but I'm sure most of you have seen movies where there's a scary scene and someone's walking down the street and there's a flickering street lamp, that's the sodium vapor lamp. All right, so here we are calculating the frequency. So we are calculating this value right here. So C is the speed of light, and this value right here will be given. You don't have to memorize that. And we have our wavelength given. So again, we're going to be calculating out our frequency. And frequency will be in seconds to the -1, which is also known as hertz. So because this chapter does have a lot of formulas, I am going to give you this formula. So here we have C equals our wavelength times our frequency. C will always be our speed of light, and again, that value is going to be given to you, 3 times 10 to the 8th meters per second, equals, now we have to deal with our wavelength. So wavelength here was given in nanometers, but it's in meters over here. We've always got to have matching units. We can't have meters on one side and nanometers on the other, so we need to do a conversion. 589 nanometers. And we need to get this into meters. So because I have nanometers on the top, I'm going to put in on the bottom here, and I'll put meters on the top. All right, what's a conversion between nanometers and meters? Anybody remember from way, way back, chapter 1? All right, so I'm hearing 10 to the 9th. Excellent. So if you can remember 9 and nano together, it is 10 to the 9th. And I see 10 to the 9 and 10 to the -9. So yes, there are two ways to write this. You could say that there are 10 to the 9th nanometers in every 1 meter, or if you prefer, for every 1 nanometer, there's 10 to the -9 meters. Either of those will work. I tend to prefer using positive exponents, so I do it this way. Okay, any questions on how we did our conversion here? Okay, so again, this is not for Wednesday's exam. This will be for your next exam. But for that exam, make sure you're comfortable converting between nanometers and meters, because that's very common in this chapter. All right, so it looks like we're going to get 5.89 times 10 to the -7, and now we're going to be in meters. So any questions on how we did the conversion or anything that we've done so far? All right, so now we're in our wavelength. So we're putting 5.89 times 10 to the -7 meters. And I'm just going to highlight this meter just so we can see we've got meters on both sides. And next up, I'm going to put our frequency in there, like so. All right, any questions on where I got those values or anything else here in our equation? All right, go ahead and take a moment and calculate out frequency. And it will be a large number, so don't be freaked out if you get a really big number. So when you get an answer, go ahead and type that into the chat box. All right, so I'm seeing lots of 5.09 times 10 to the 14. Excellent. Excellent. All right, how are we doing? Anybody getting something different here, or anyone want to see me do the calculations? All right, so the unit seconds to the -1 is the same as the unit hertz. But of course, if the problem asks for hertz, you want to give it in hertz. So 5.09 times 10 to the 14, and we can write hertz like so. I do have a habit of crossing my z's. That's why that little line is there in the middle of the z. But any questions on anything here about how we found our wavelength? So what's the problem saying? So the problem was asking us what the frequency of the light was given this wavelength. Was that your question, Eddie?
More like, is it saying that it'll 5.09 times 10 to the 14th, I guess seconds? That many seconds it'll, do you know what I'm trying to say?
Yes, so this is a measure of the wavelength, and it's kind of crazy when you think about it. So I gave you the example when you were sitting on top of this wave, either in your boat or magically floating, you were counting how many times the waves pass you, right? But light travels so fast that if you were counting a light wave and you were able to count this fast, you would count 5.09 times 10 to the 14th waves passing you every second. It's kind of crazy. Yeah, it's kind of crazy to think about that high of a number of waves passing you every second. But if you were standing under that flickering yellow light in the monster movie, the light's really hitting you that fast. So does that sort of help out?
Yes, thank you.
Oh, you're welcome. It is really crazy to think about the light is hitting you that fast. So that many waves are passing you every second. And most of our visible light does have that high of a frequency. Oops. So you are really being completely assaulted by these light waves every second. All right, so other questions before we move on to another one? All right. So next up, calculating the wavelength. So it says, what is the wavelength of an electron moving with a speed of 5.97 times 10 to the 6 meters per second in angstrom? And the mass of an electron is 9.11 times 10 to the -31 kilograms. So here is going to be our formula, and this again is going to be given. We have a lot of formulas in this chapter, and I think it's just too much to have you memorize them all. So over here we have our wavelength. Up here we have what we call Planck's constant, and that is right over here. And again, Planck's constant is going to be given. Now the tricky thing on the bottom is this M right here is going to be the mass in kilograms. And it's got to be in kilograms because Planck's constant has a joule in it, and those joules have kilograms hidden inside of them. So whenever you've got joules, you're dealing in kilograms. And then the other tricky thing right here is this V is not velocity. I'm sorry, this V is not the frequency, it is actually the velocity or the speed. So those of you who've had physics know the difference between velocity and speed is velocity is directional. So if you were driving, you were going 25 miles an hour, that's your speed. If you were going 25 miles an hour north, that's your velocity. So it's got a direction to it. So here in this problem, we can get our wavelength given that we have our Planck's constant, we know our velocity, and we know our mass. So let's give this one a try. All right, so it says, what is the wavelength? So we will be looking for the wavelength. And then we're going to start filling into our formula. First off with Planck's constant. And Planck's constant right over here is 6.626 times 10 to the -34. And with Planck's constant, Our units are joules times seconds. And next up, we need our mass in kilograms. And that was given right up here, 9.11 times 10 to the negative 31. And then we need our speed. And our speed is 5.97 times 10 to the 6. And it is in meters per second. Okay, so any questions on how I set this one up? So I see a question from Tasso. What is the s to the negative 1 unit? Do you mean, and let me jump back here for a second, do you mean that s to the negative 1 equals a hertz? Yes, so that is frequency. It is frequency that is s to the negative 1, yes. All right, so any questions on how we set this one up? You're welcome. All right, go ahead and take a moment and calculate out our wavelength. So first just calculate it out in meters, and then we will convert to the angstroms together. So when you get a value, go ahead and type that into the chat box. All right, so I'm seeing 1.22 times 10 to the negative 10. How about the rest of you? Did you get something similar, different? All right, so it looks like lots of you getting similar answers. All right, so any questions on how we got this answer? Anyone want to see me calculate this one? Okay, so before we go on, I want to show you how the units work out. So what I want to do is replace the joules with what a joule is. So kilograms times meter squared divided by second squared, like so. So what happens is the kilograms cancel out. And let's see. We're going to cancel out our meters. We're going to cancel out one of the seconds, and then we'll cancel out the other second, and we will be left with those meters right there. How does it all cancel out to the meter? Does this answer your question, Eddie, how it's canceling out? Yes, okay. Other questions about these units, about how things are canceling out?
Yeah, could you explain the meter one too?
Explain how it becomes the meters right here.
Oh, so it's just a single meter.
It is, because the way the meters canceled is the square canceled with the meters at the bottom. Because you had meters squared on the top and meters. Oh, go ahead.
Yeah, and then since there's both there's 2 seconds and then there's a second squared, then everything cancels out for that.
Exactly. So you're only left with 1 meter. Yep.
All right. Cool. Thank you.
You're welcome. So yes, so Andrew is right. So one of the 2 is gone. Yes. All right. Other questions about how those units cancel out? All right, so let's convert our meters into angstroms. So angstroms are sort of an unusual unit, although where they're used is for very, very small things. So sometimes we use angstroms when we're talking about the radius of an atom, or sometimes we use it when we're talking about a bond length. So this I will be giving to you. So this conversion is given, but I do want you to be able to use it. And it is 1 angstrom equals 10 to the negative 10 meters. The other way you could think of it is there's 10 to the 10th angstroms in 1 meter. So either way you want to think about this. So I'm going to do our conversion. So 1.22 times 10 to the negative 10 meters. And I'll go ahead and use this conversion that's typed out here. 1 angstroms is 10 to the negative 10 meters. So for every 1 angstrom, there is 10 to the negative 10 meters. So if we do this calculation, we'll end up with 1.22 angstroms like so. And the angstrom does have that little circle above it that's part of the symbol. So any questions on how we found our final answer in angstroms? Okay, so thank you for suffering through a lecture that is not covered on your upcoming exam. I know sometimes that is tough, but any questions about anything that we went over today? Okay, so what I want to do is give you guys a 10-minute break, and then we're going to go through the lab. And after that, I will be here till 9:45. If you want to stay with me, you can work on the lab, you can work on homework. You can also just ask me about questions that might be relevant to the exam. So I've talked to a few of you who say that you'd want some extra practice problems. So after the lab period is over, if you want to say, hey, can you give me some practice problems on stoichiometry with enthalpy, or whatever it is you want to do, we can turn it into a problem-solving session to help you study for the exam. So whatever it is you want to do between the time our lab is over and 9:45, I'm here to help you guys. So just think about that. I know most of you like to rush out after the lab is over, but just think about staying and getting some extra help before the exam. So let's go ahead and come back at 7:25, and we will spend some time on the lab, and then it'll be up to you whether you want to stay, get some help, feel so much better about the upcoming exam, or you can leave. All right, so go ahead and take about a 10-minute break and come back at 7:25.